Okay, good morning. We will talk about the molecular weight, and I hope that you have already read about this molecular weight and how to measure the molecular weight. Okay, so let me ask you several questions. Now, in this chapter, I said we are talking about the molecular weight, right? Why we are measuring the molecular weight in the polymer? Why we have to measure the molecular weight in the polymers? Tell me. Well, he said that we need to know about the size of the polymers, right? Why? Why we have to know about the size of the polymers? Talk in English, please. Enough degree? Well, perhaps the first question about why we have to measure the molecular weight, and you said about the size. Okay, size is very important in this case. Does polymer has the same size? No, that's not. So we have a different size of the molecules in your polymer batch. Okay? If you obtain the polymer, size of each molecule is different. Okay? In the reactor, they grow their molecular weight, and they grow their size of the repeating units, and all of them are in different sizes and different molecular weights. That's why we have to measure the molecular weight in statistical way. Okay, so we have to treat this molecular weight term as a statistically. Okay? So we have to talk about the average molecular weight rather than absolute molecular weight. We are not able to measure the absolute molecular weight of each polymer chain in this case, right? That's the brief summary of what we are going to talk about it. Do you know about the relative method of molecular weight measurement and the absolute method? There are two ways of measuring each molecular weight. Okay, I think you have already learned about light scattering method, colligative method, and end group analysis. And those methods of measuring the molecular weight that you have learned in physical chemistry or the general chemistry are called absolute molecular weight measurement method. But it's very difficult. It should be applied to measure each molecular weight of small molecules with the same size. Okay, each molecule has the same size, and you have to know about absolute molecular weight. But in our case, we have a different molecular weight of each chain, and we have to treat it as a statistical way, so that we have to know about the relative method, okay? Such as the viscosity, such as the gel permeation chromatography, are the very much convenient way of measuring the molecular weight of polymer, but we have to know about the references, standard that we are going to talk about. So that's the things that we will talk about it. What about the properties of the polymer? Does polymer with a large molecular weight or a long molecular weight versus the polymer with the small molecular weight have the same property? No, it's not. Perhaps the properties such as the mechanical property or viscosity or viscosity is a solution property are all different if you have a different molecular weight. So the molecular weight influences the property of your polymers. So these are the questions that I have raised at the beginning, and these are the things that we will talk about. Okay? First of all, let's talk about the molecular weight. Okay? Molecular weight measurement. Now I have drawn the graph here, where the x-axis is something like m. M means molecular weight, and you have a subscript n, v, w, and z. Okay, indicating that you have a different type of molecular weight. Anyway, I think we will talk about this, how to measure the Mn, Mw, Mv, and Mz, and these are the distribution of the molecular weights. Okay? So when you obtain the polymer, if you can draw the line in the x-axis, and y is the weight or the intensity of, or you can say that this is the moles of each molecules, meaning that, for example, if you have a molecular weight of 1,000 at this point here, 10,000, 20,000, 100,000, stuff like that. So you increase your molecular weight of each chain, and each chain has how many molecules, such as in this case 100 molecules, in this case maybe 70 molecules of 1,000, 10,000, in this case maybe 100,000 molecular weight chain may have 100 the chains and stuff like that. So if you draw this line, we have a distribution of molecules in your polymeric system. Okay, it could be pretty wide or a broad distribution, or it could be quite narrow distribution, depending upon how you are making the polymer. Typically, if you make the polymer in the space, okay, in the space shuttle, molecular weight is very narrow. Because you don't have any gravity effect. Where if you are making the polymer on the Earth, then we always have the distribution of these polymers just like this. Okay, so it's quite interesting, and I said that the maximum point here is usually called Mn, and Mn is always lower than the rest of the other molecular weights. And the next larger molecular weight is Mv, Mw, and Mz. Okay, so this is the way of measuring the molecular weight in terms of the number average, viscosity average, and weight average, and Z average. So we'll talk about in detail, of course, but when you look at this distribution, the largest point is always the Mn, and next one is Mv, Mw, and so on. So Mw is always larger than Mn. Okay? But if you have narrow distribution of the molecular weight, such as the polymer that you are making in the space, with a very narrow distribution, Mn, which is the maximum point, and Mw is almost the same. Right? So Mw divided by Mn, or Mn divided by Mw, whatever, okay? If it's equal to 1, then means that you have a very narrow distribution of your molecular weight. Right? Mn, Mw. Mn and Mw is almost the same, right? With a narrow distribution of the molecular weight. But in this case, you have pretty much the gap between the Mw and Mn, so that we call this type of the polymer as a polydisperse the polymers. Polymers with a polydispersity. In other words, you have a very broad distribution of the molecular weight. You have a large number of, you have many large molecules, and also many smaller molecules as well. those large molecules and small molecules will affect your property and the viscosity and your final property of your materials. Whereas a narrow polymers with this type of a very narrow distribution have a very distinct viscosity. You don't have any distribution of your property, but you can predict your property depending upon your viscosity of your materials. Okay, so we'll talk about it anyway. Anyway, I think we are talking about the average molecular weight. Okay, average molecular weight. In the case of small molecules, low molecular weight components, we define that molecular weight m is equal to the weight of the sample divided by the moles of the samples. Okay, if you measure the weight of your molecules and divide by the number of moles, then that's what the molecular weight of polymer is, the smaller molecule is. So m is equal to W divided by N. The same analogy can be applied to this polymer in this case, but we have to know how we can average these molecules by number, or by viscosity, or by weight, or by some method called Z. So we have 4 ways of measuring the average molecular weights. If you put the average, then we always put some line on top of here. Okay, I don't have I just made a mistake here, but you just put the bar here, indicating the average. M bar is the average molecular weight, and the type of the subscript is how you can treat your molecular weight. I mean the average. Okay? So let's talk about the average molecular weight. First of all, we said that we have a Mn, right? Mn is the number average molecular weight. I think you have to put the bar here, Mn, and Mw. And Mn and Mw are the most interesting and most widely used average molecular weight in the polymer systems. So we will focus more on the Mn and Mw. Mn, as it says, number average molecular weight, indicating that you have an average molecular weight by treating this calculation with a number of a mole or moles of the polymeric systems. Moles. How many molecules do you have? Whereas weight average molecular weight is what about the weight of your molecules? You see, weight and number is different. If you look back, weight and number are different, right? W and N are quite different. So here in this case, we average the molecular weight by N, number. In this case, average molecular weight by weight of your sample. Okay, so let's talk about the Mn, and Mn considers the number of molecules of each size. So if you have different sizes of molecules, okay, each molecule may have a molecular weight with unknown molecular weight, which is X. Okay, so we call this Mx. Or each molecule, could be Xmer. X molecule. Xmer means that X could be any number. X could be 10. X could be 10,000. X could be 100,000. Depending upon your X, the magnitude of X, we have different molecular weights. Okay. Here in this case, but in this case, we consider the mass of the molecules, the weight of the molecules. And the equation looks something like this. Mn bar, of course, is equal to W divided by N. W is the weight of your total Xmer, okay? divided by the total number of the molecules in the sample Xmer. Although it looks quite similar, but we have different numbers, different size of each molecules. So Xmer weight, the weight is what we can divide this by 2 is Wx weight of the Xmer, and X could be any number, starting from 1 to infinity. So if you summate this Wx in this case, or the number of moles Nx, if you summate this is the correct equation, right? And weight, as you know, is what? Weight is n times m, where m is equal to W divided by n. So that if you summate this nx times the mx, where x is equal to 1 to infinite, then this is the next or correct equation. And if you look at very carefully, this number here is mole fraction. Okay, this is the mole fraction. So if you summate this, the mole fraction times the mx, the mass of the Xmer, then you can obtain the Mn, or average molecular weight. Okay? Although it looks a little complicated, it's a very simple equation, whereas Mn bar can be defined as the weight of the Xmer divided by the number of Xmer sample. So that you can multiplicate the mole fraction of Xmer times the mass of the Xmer sample. Okay? That is the definition of number average molecular weight. What about the weight average molecular weight? Weight average molecular weight is the one that is almost the same, but instead of the mole fraction, you can multiplicate the weight fraction. Instead of mole fraction, the weight fraction of the Xmer times the mx, as you can see here in the bottom. MW bar is defined as the total weight of the sample divided by total weight of the Xmer sample, instead of the total number here. Okay? And if you redefine this, you can redefine this. And if you look at this equation, this is the weight fraction times the mx versus the mole fraction times the mx. Okay, so if you know the weight fraction, then you can obtain the weight average molecular weight instead of the mole fraction for the number average molecular weight. So mole versus the weight are the important factors influencing your calculation of the molecular weight. You have the same polymer, but by defining the different definition or different method of measuring the molecular weight, you have 2 different molecular weights. Okay? Anyway, by definition, MW is always higher than Mn. That's why we obtain this type of curve. No, this is the typical curve of your polymer systems, where you have a certain number of molecules with a certain number of molecular weight, and a certain number of molecules with a certain number of the molecular weight, and that's why the MW is always larger than the Mn. Okay, by just measuring calculating different methods. So Mn and Mw are 2 different ways of measuring the molecular weight of the same polymer. Okay, you do not have the different polymer, but you have the same polymer, but by calculating 2 different ways of the calculation, you have 2 different molecular weights with the same polymer. But we have another 2 different molecular weights as well, MV and MZ. So let's talk about MV and MZ. But MV or M eta is a viscosity, or MV is a viscosity. So this is the viscosity average of molecular weight. So if you know the viscosity, then we can calculate the viscosity average molecular weight. Well, the Z average molecular weight can be determined by the centrifuge method, but it's not very well used in these days. But I just would like to let you know that, well, we have the G average molecular weight, but this is just by definition. Okay? Anyway, if you learned about the polymer, you were always asked whether you know about the 4 ways of measuring the average molecular weights. Okay? If you go to the company, or if you take an examination, oral examination, and somebody can see your transcript and the polymer chemistry courses were taken in your transcript, then you're always asked, tell me about molecular weight, average molecular weight. And you should start talking about Mn, Mw, M-eta, or Mv, or Mn. Okay? Particularly Mn and Mw are most important 2 different ways of measuring the molecular weight. Okay? So if you take a look at at the end of the chapter, you have several problem sets. How to calculate the average molecular weight, Mn and Mw. So please solve some of these questions and calculate by yourself, and that way you will be much more understandable about how to calculate and how to define this Mn and Mw particularly. So please do so, and they will be much more helpful in your midterm examination. I'll not give you the assignment, but I hope that you will be able to exercise those questions. Now, the 4th important definition is polydispersity. Excuse me, the fifth one. You should know about Mn, Mw, Mv, and Mz. And the 5th one, important aspect, is polydispersity. And I think I have already talked about this. Polydispersity means how broad or how narrow your molecular weight distribution is. Okay? In this case, I told you that Mn and Mw is almost the same. And polydispersity means that what about the Mw divided by Mn? Okay? Mw is always larger than Mn, so that if Mw divided by Mn is larger than 1, just in the case of the first distribution cases, we call this as a broad distribution versus the narrow distribution. This molecular weight distribution, and the molecular weight distribution is abbreviated as MWD. Okay, MWD. So the first graph says, we have a polydispersed molecular weight distribution, or the broad molecular weight distribution, where the polydispersed is larger than 1, whereas Mn versus the Mw is equal to 1. In this case, we call this as a narrow molecular weight distribution or monodispersed distributions. Monodispersed. Dispersed is just 1. Okay? We don't have any the distribution in this case. Okay, I think this is the same graph that I have shown you in the first cases. Let's talk about the property. Okay, let's talk about the property. Now, I told you that large molecules, the polymer with the long molecular weight or large molecular weight versus the polymer with the smaller molecular weight or the short molecular weight may have a two different property. Okay, excuse me about the Korean words, but the polymer is just like in Korean term, 엿 같다 그래요. 고분자는 엿 같다 그래요. 그러니까 계속 엿 같다 그러면 여러분 계속 웃을 텐데, 하여튼 여기 외국인도 있으니까 아마 잘 못 알아들을지 모르겠는데, 어쨌든 고분자는 이건 엿이라고 생각하면 돼요. 그러니까 그 엿이 어때요? 끈적끈적하고 막 이렇게 늘어나잖아요. 꼭 그렇게 돼. 꼭 그렇게 돼. 그래서 비스커시티하고 이제 비스커시티가 늘어나면 그건 분명히 그거는 고분자가 되는 거예요. 모노마를 집어넣으면 모노마는 엿 같지 않은데 고분자가 되면 엿 같이 돼버리는 거예요. 그래서 끈적끈적하고 이렇게 조청처럼 이렇게 돼버리는 건 그런 분자량이 분명히 늘어난다는 뜻이에요. 비스커시티가 분명히 늘어난다는 뜻이에요. 비스커시티가 늘어나면 흐름이 흘러갈 수가 없잖아요. 그런 특성이 꼭 고분자에 있어요. Okay, sorry about it, but anyway, I just talked to you about the viscosity increases as the molecular weight increases. The reason why we have increase in the molecular weight and change in the property, particularly in the viscosity, is something like this. If you have a long chain, okay, starting from smaller molecular weight, well, this is the small molecular weight. Maybe the molecules will gather together to have a long chain, but if let's say the molecular weight is like 10,000 for your smaller polymer, okay, molecular weight polymer. But if you increase the polymer molecular weight, then your molecular weight increases and it gets very much entangled. Okay? If you have a long polymer chain, your polymer chain will be much more, what you call in Korean is like a 꼬인다 그러죠. 뭐 실이 꼬이듯이. If you have a long polymer chain, you always have some problem with the linearity. This was much more entangled. What we call the term is entanglement. So the polymer will be getting entangled. So low molecular weight component and large molecular weight component are two different property. With that, if you have a long polymer chain, the first property changes is the mechanical property. Mechanically, because of the entanglement, your polymer chain has a very strong material, becoming very strong. For example, perhaps you have learned about the polyethylene, right? Polyethylene. You have ethylene, CH2, CH2 units will be combined together to have a long polymer chain. Usually the polyethylene may have a molecular weight around 1,000, okay, 10,000 or 100,000, stuff like that. That's the typical polymer molecular weight of the polyethylene. But if you wanted to use your polyethylene in your hip joint, in the biomedical application, this should be very strong because your polymeric material should not be degraded and should not be mechanically, debrided. So your molecular weight should be much more higher than 10,000 or 100,000. In those polyethylene for biomedical application, the molecular weight is typically in the range of millions. Okay, that means that you have a much more stronger entanglement, so the mechanical property should be much more higher. And even though you have the same repeating unit the same, N is different. Okay. Next property is about the impact strength. Entanglement always influences your, the other properties such as impact strength. Impact strength means that if you impact, if you hit your polymer, in some case your polymer will be broken, right? if you have a low molecular weight components, if you have impact, if you stress them, your polymer may be broken. But in this case, because of the entanglements, because of this entanglement, if you stress them or if you impact, still resist. Okay? So entanglement is quite important aspect of the property in this case as well. Impact strength could be applied in the case of plastic as well. If you have a certain plastic, but if you add the plastic is usually glassy polymer, but if you add the rubber in your glassy plastic stages, your polymer will have a higher impact strength because rubber absorbs the energy. Impact is an energy, and you absorb the energy, so that the material with the glassy and rubbery part will have a high impact strength. So, for example, ABS, acrylonitrile butadiene styrene, ABS resin have a butadiene units, which is a rubbery part in the acrylonitrile, and the styrene part. Styrene is a glassy polymer, okay? And if you add the butadiene units, you absorb the heat, so that your plastic is quite impacted, strong upon impact. So about 20 years ago, several electronics company, Samsung and LG, came to us how they can improve their impact strength of the refrigerator. The inside of the refrigerator, there are some problems about 10 years ago when they started to produce this ABS resin. And when you close the door of your refrigerator, the plastic inside of them have some cracks, okay? Have some cracks, even though they did not put the impact them, so that there is a lot of problems of those plastics a long time ago. But right now, I think they improved a lot and impact the strength of the plastic of ABS resin, which is a very typical the plastic right now in Korea because of the electronics industry. We have a lot of improvements in that as well. Chemical resistivity, chemical resistance is much more stronger if you have more entanglements, okay, in this case. However, because of the very high viscosity of this entangled polymeric chain, we have a difficulty in flowing of these fluids, okay, in flowing. In other words, this high viscosity is in many cases the advantages, but in some cases it's difficult to fabricate. In other words, if you wanted to make this type of the plastic, you have to apply the heat, right, and flow through. You have to make it melt and flow through some of the mold, okay, metal mold, and let it cool down to crystallize them, right? But during those flowing process, where the rheology should be very important, rheology. Rheology is the study on the flow of your materials. Okay. If you learned about the reaction engineering, or the unit processes, or mass transfer, or heat transfer, or those transport phenomena, you always have some type of pipes, right? And inside of those pipe, you have a fluid, right? Fluid, and fluid should go through those pipeline. And if the material has a low viscosity, then you have a low resistance to flow upon the wall, right? So in the center line, you have a concentration gradient, of course. So the center is much more faster than the wall. because of the resistance and the war resistance, right? But if you have a very high viscosity, then the flow is much more restricted because of the resistance on the wall, of course, and also in the center line as well. Okay? And therefore, it's very difficult to make a product because of the reduced flowability if you have a high viscosity, high entanglement. Right? Anyway, that's one of the obstacles of the fabricability of the materials. I think this is almost the same time. Because of the entanglement, you have very much difficulty in fabricating your materials, in other words. So as you increase the molecular weight, your strength increases, of course, but it's not increasing linearly, but it increases exponentially. So there are certain points where your molecular weight is about the same, and the increase, in other words, the slope increases at the beginning, but increase of your slope is coming down. So derivative of this curve is about the same. So slope is about the same, and you have to cut if you increase the molecular weight, your flowability is much more reduced. All the mechanical property increases. So there are certain points that you have to cut your molecular weight, right? Okay. Anyway, although we have 4 different molecular weights, okay, Mn, Mw, Mv, and Me-tar, and polydispersity, and I think we have talked about the property, effect of molecular weight on the property of your materials. Now, we can start talking about how we can measure the molecular weight. Okay, we have already defined the molecular weights. Okay? As we have already seen the glass transition temperature in our chapter 4, if you remind how we can calculate the crystallinity, perhaps you can remember 2 ways of measuring the crystallinity, right? The first is DSC, right? DSC, melting behaviors of the crystals, and the second way is diffraction, right? Wide-angle diffraction methods, so that if there is any peak, then you can integrate those peaks and calculate the crystallinity. Just like those type of methods, we can also measure the molecular weight of each polymers. Now, we have listed here, number average molecular weight can be calculated by the end group analysis or colligative property. End group analysis is the one that your chain end, okay? Assuming that you have functional groups, you can titrate them or chemically measure how many moles of your functional groups are present in your polymeric systems. So if you can, because you have 2 ends, in the case of linear polymer, 2 ends, you can, if you know about the number of functional groups, then you can calculate how many moles of the molecules. In that way, you can calculate the numbers of molecules and the average molecular weight, of course, by knowing the numbers. Colligative ways are the ones that there is presented in your the general chemistry courses, and this is ideally you can calculate the boiling point elevation or freezing point depressions of the small molecules, but in the case of polymers, it's not easy. Okay, it's not easy. So although this is the ideally suggested a long time ago, is not quite widely used these days. But weight average molecular weight can be calculated by the light scattering method, which will be introduced in the next slide. So I will tell you what is this light scattering. meaning that you expose your polymer sample with the laser so that the scattering pattern, scattering angle, by knowing the scattering angle, you can calculate the weight average molecular weight by this lightest scattering method. Viscosity average molecular weight is a very simple way because the polymer is like a yacht, okay, yacht 같은 거죠. So by measuring the viscosity, you can calculate the MV, okay. You know the molecular weight distribution, molecular weights and molecular distribution very easily by GPC, gel permeation chromatography. And this is the relative ways of measuring the molecular weights. Now, first the three, 1, 2, and 3, and the fourth, the final one, are called absolute molecular weights. End group analysis, colligative, light scattering, and centrifuge are called absolute molecular weight, whereas the viscosity and GPC are called relative the methods, okay? Absolute method and relative method. Absolute methods are, of course, very precise, but it's difficult. So these days, the relative methods are very widely used, and I will introduce these two methods in more details. But first of all, I think I would like to introduce a light scattering method. Light scattering method is the instrument, and in the third floor of the Shinsoje here, we have a light scattering instrument, so that if you put your sample here, and there is a helium and neon laser, and this is a schematic. If I look at from the side, okay, this is the side view, and this is the top view. Okay? I can take a look at from the top. Okay, in this case. Anyway, you have an optical slit, so laser is exposing to your slit through the slit and to the sample, and if there is no sample, laser will transmit through the solution, or if there is any polymer, then the laser will get a scattering, okay, scattered, or the scatter or refract those light, right? And the scattering pattern is different depending upon your molecular weight, right? So by knowing those, the light scattering, the principle, which is called the Tyndall effect, then you can calculate the weight average molecular weights. If you look very carefully, you can take, in your textbook, you will be able to find in more details about the light scattering methods to measure the weight average molecular weight. Now, let's talk about the viscosity average molecular weight and the GPC, the methods. Okay? This is the green one is a polymer solution. Okay, we have a glass, the tube. We have a glass tube. We have a glass tube, and you put your polymer solution here, and using the tube, using the spheroid, you can put your polymer solution on top of this line, and if you release those, the closed system to the open system, then because of the gravity differences, the green line will move to here, whereas a green line in the left-hand side tube will increase. So there should be a balance. Now there are two lines here. This is the line here, and this is the line here. And through the line, you have a capillary. You have a smaller capillary inside of this tube. Now this solution will pass through this capillary. If you have a larger capillary, okay, larger capillary, the time to go from this line number 1 to line number 2 will take a very short time, right? If the capillary is larger. If the capillary is much smaller, then time from passing through this line number 1 and line number 2 will take a long time, right? So depending upon the capillary, the diameter, time of your dropping your solution from line number 1 to line number 2 will be different. Now, if you take the same capillary, okay, and with two different solutions, one solution has a low viscosity, and the second solution has a high viscosity. Okay, for example, you just measure the dropping time from here to here through the same capillary using just a solution, just a solvent. Okay, solvent will take pretty much short time, whereas the polymer inside your solvent, which is a viscous solution, will take a long time dropping from here to here through this capillary. Okay, understandable? So perhaps you will not. So I will. Let's go over to do the virtual experiments. Okay, in the next slide, I think we have captured the virtual experiments. So let's say that we measure the concentration, we measure this time of your dropping of your solvent first, and later on the concentrated polymer solution, the dropping time from here to here through this capillary. So let's say that at a given concentration, with a zero concentration, for example, solvent, okay, it took T0 time, okay, with a zero concentration, with the concentration 1, C1, it took T1. At C2, it took T2, stuff like that. So you measure the time, and as you increase the concentration. So the time which takes this dropping from line number 1 to line number 2 through capillary will depend upon the concentration of polymers, right? So assuming that the ratio of this dropping time here, T divided by T0, you know what's the T means. The T could be T1, T2, and T3, right? T0 is dropping time of your solvent, okay? And T divided by T0 will be equal to viscosity of your polymer solution divided by viscosity of your solvent. And is equal to, we define this as a relative viscosity, okay? Relative viscosity, eta R. Eta R. Eta R, eta R minus 1, or eta minus eta 0 divided by eta 0, whereas eta divided by eta R, this is eta R, minus 1 is defined as eta specific. So just if you define this as manipulating this equation, just by measuring the T divided by T0, or T and T0, then you can come up with the eta specific. Now, eta specific, but divided by concentration, and the concentration could be 0 to any number, is defined as intrinsic viscosity. So from this equation, we know that we can measure T and T0. We know C, because C depends upon the T. I mean, T depends upon C, of course. So by measuring the T and concentration, you can come up with eta, intrinsic viscosity. Now, intrinsic viscosity, this is the concentration, and you have some numbers. although we have a difficulty in going over to the actual results, anyway, we can come up with T, T0, and C0. Right? Now, when you plot C here, C, C1, C2, C3, stuff like that, and this is a C0, okay? And eta can be calculated when you know eta specific divided by C. Okay? So eta reduced or eta specific divided by C, at different concentration you come up with the different points, and if you can extrapolate them at an infinite dilution where C is equal to 0, the point intercept at C is equal to 0 is defined as eta. Okay, eta specific. I mean the eta intrinsic viscosity. So intrinsic viscosity, again, intrinsic viscosity can be calculated by knowing T0, T, and C. And if you plot those points, in here, then you can, if you extrapolate them, then you can come up with eta intrinsic. This eta intrinsic is very important to measure the viscosity average molecular weight by knowing this equation. If you look at this, eta intrinsic viscosity is equal to K times M to the A. And this K and A are constants. And I will show you what this K and A means. And what about the magnitude of this K and A? This equation is called Flory-Huygens equation. I told you that Flory is the father of polymer chemistry. Flory-Huygens equation, or sometimes this equation can be defined as a different, named as a different equation as well. But this is what they call the Flory-Huygens equation. So if you know the intrinsic viscosity, and also by knowing this K constant and A constant, okay, and you can come up with M. If you look at if you take this logarithmic of this equation, then this will be log eta, log K plus A times log MA. So these the eta has a logarithmically dependent upon M, okay, molecular weight. So by knowing K and A of your system, and K and A, A will be about 0.5 for this case. If you have a pro-solvent, polymer with pro-solvents, and A could be 1.7 for your rigid rod like polymers, and K could be a Huygens constant and could be in some numbers, and K and A can be measured and can be was suggested for non-polymer systems. So if you look at the textbook over certain polymer systems, your K and A are given. So by measuring the viscosity and knowing this K and A, you can come up with M, okay, molecular weight, by measuring the viscosity. Okay, so this is how we can measure the viscosity. And I think this equation is about the same. You can specifically, the eta specific divided by concentration is equal to eta, which is intrinsic viscosity, plus K times and stuff like that. And if you plot the C concentration versus the eta specific divided by C, then you can, the slope will be K, and intercept, y-intercept is eta. So from this y-intercept, by the extrapolation of this C versus the eta specific divided by C, you can come up with the intrinsic viscosity values. Okay, so this equation can be the same as this curve, right? Anyway, this is the how we can measure the viscosity average molecular weight. And I will show you the viscometer. This is a very simple system. We have automatic viscosity measurement system. So by knowing your the solvent, the dropping time of a solvent, and dropping time of your polymer solution, and this is connected with a computer at a given temperature, which is controlled, and overnight, if you come up with tomorrow morning, you can get the value of the molecular weight by measuring the viscosity automatically. So we have the system, and I will show you later on how we can measure those viscosities. Next topic is about the weight average molecular weight using the GPC. Okay? GPC, gel permeation chromatography, is a kind of a liquid chromatography. Okay, liquid chromatography. We have 3 GPC here in this floor, 3 GPC, and each GPC costs about $100,000, and it's very expensive. But the different solvent uses the different GPC. In other words, we have a water GPC, we have NMP GPC, we have THF GPCs. So depending upon the solvents, we need to use, and we need to use depending upon the polymers, we need to use the 3 different systems. The principle is very simple. In the liquid chromatography, we need to have a column. Okay, column is very expensive and very important. Inside of this column, we have the beads, polymer beads, polymer particle, polymer bead with the porous nature inside. Okay, this is the porous, indicating the porous nature. But we have polymers with the entanglements coming in. We have a small molecular weight components, and we have larger polymer components. Okay? When the polymers with the different size are coming into this column, and it meets with the bead with the porous layer inside. And if you think about it, the larger or entangled one will come up with here, whereas a smaller one getting into this porous layer. So the smaller molecule are trapped, whereas the larger molecule will pass through, because it will not be entrapped. Okay? So large molecules comes first, whereas a smaller molecule first trapped inside with this porous layer, porous bead, but come up later. Okay? So this is what they called size exclusion principle. Oh, here we go. This is what they call size exclusion principle. So large molecule comes first, whereas the smaller molecules comes later. Okay? This is the column. Column cost about at least $5,000. And this bead is made of porous polystyrene usually. Okay? Porous polystyrene. It was filled, and first of all, we just passed the solvent, and from left to right, solvent is flowing, and later on, the polymer solution was injected through this injector, and the larger molecules comes first, and smaller molecules comes later, because of the size exclusion principle. And what we can have a typical graph is that as a function of time, you have generally molecular weight distribution. Large molecule comes first, whereas a smaller molecule comes later. Okay? And this y-axis is the number of molecules. So with a large molecule, with the small number, or perhaps this molecule, this molecular size. So time means the molecular weight. Okay? And y means number of molecules. So if you plot in different way, the molecular weight is different from the time scale. And anyway, you can obtain this type of the molecular weight distribution curve. If you know the molecular weight distribution curve, you will be able to obtain Mn, Mw, and you get the polydispersity. If you obtain this molecular weight distribution curve, the GPC will automatically calculate Mn, Mw, Mv, and Mz. Okay, so you don't need to go through with a very complicated calculation steps. So computer will do the calculation for you automatically. So I can show you, this is the typical GPC, one of the GPC in the ninth floor here. And we have the detector. We have heat controller. We have detector. We have a column inside. So inside of this serial column, we have several columns, and we have reservoir. We can have automatic sampler. So you put the samples, you put the polymer samples here and put it in. And if you can just order measure the molecular weight of each sample, the computer will tell you later on or next morning, you can come up with the molecular weight measurements. So this is the typical example of the one of the GPC. And I told you that we have the 3 different GPCs. The reason why we have 3 different GPCs is that when you are using the THF, tetrahydrofuran, tetrahydrofuran is a very typical solvent with a low boiling points. It's very similar to acetone, okay? So that most of the polymers can be dissolved in the THF. We use the THF as a standard solvent. But in some cases, we have to use water if it's dissolved in water. And in some cases, we have to use NMP or N-methylpyrrolidone or dimethylacetamide. And so these are 3 different scales, 3 different solvents can be used. When you use this THF solvent, and if you wanted to change your solvent, you can do that, but the accuracy of each measurement after you're changing your solvent will cause a lot of problems, because whole line through this, from this polymers, from this reservoir to this column and through a detector, all through the detector should be in the same polymer, same solvents. So it took a long time to stabilize this system. So instead of taking a risk, we decided to have 3 different the GPC systems. This is the simple schematics. You have reservoir of a solvent. You usually have to degas them, meaning that the gas bubble is very critical, because if you push the solvent through the pump, you get through through the pump. This solvent will go through these columns, and at a certain period, you inject your polymer solution by your hands or by automatic auto sampler. You can have a detector. Detector could be refractive index detector. Refractive index is, I think you know in Korean word, meaning that each molecule, the water, solvent, polymer with the low molecular weight components and large molecular component may have a different refractive index. Okay, the water, I think it has 1.333, something like that. Whereas if we add the polymer with a long chain and small chain, refractive index will increase anyway. So by knowing the difference in the refractive index, depending upon your molecular weight of your polymer systems, then the difference between these two different refractive index can be detected. Or if you have double bonds in your system, you can use the UV detector as one of the detector, because UV, ultraviolet light, can detect the absorbance of your the double bonds. Okay? You can use different types of the detectors, such as a light scattering detector. Okay, if you add the light scattering detector instead of the differential refractive index detector, you can obtain the absolute molecular weight of your samples, right? Because light scattering, the method is what we learn is an absolute molecular weight. And light scattering detector is very nice, but of course you have to pay. It's about the same cost of the full system with this detector. Anyway, you get the molecular weights as a function of time and the time scales. So this is the typical way of measuring the molecular weight using the GPC. We don't have time to show you the GPC, but the next Friday, this coming Friday, I think we can take a little bit of time to show you the viscometer and GPC before we start our class. So come to class, and I will show you about 10 to 15 minutes showing you GPC and also DSC and other instruments here on Friday morning. Okay. And also yes, lab tour for about 15 minutes, I guess. And again, as I have announced to you last week, we're going to have a first quiz on this coming Saturday morning at 9:30, right? About the structure and the polymer naming. Okay, you're given with a name such as a polyvinyl chloride, and I'll ask you what is the polymer structure with the repeating units. Okay, or you're given with a polymer structure such as PVC, and you asked what is the name of this polymer. Okay, so this is the typical ways of the questions in your quiz. So please do the exercise at the end of your chapter 1, and naming names and the structures. Okay? You can obtain the previous examination sheets or the problem sets of the previous classes, and it will be of course helpful. Okay, so I'll see you on Friday morning. Thank you.